You're signing up for an app. You type in the perfect username and hit enter. Instantly, the app tells you it's already taken. But think about the scale for a second. Did the system just successfully scan 3 billion individual records in a fraction of a millisecond? If it actually tried to do that, the physical servers would melt. A single database has hard limitations on its CPU, RAM, and network bandwidth. Hitting it with a massive global query volume all at once would cause a total hardware collapse. Linear searching is physically impossible at this scale, which means to give you that instant warning, the system must be bypassing the act of searching entirely. The mandatory first step for scaling any massive dataset is dividing it into smaller, isolated containers. Engineers call this process sharding. Think of a densely populated city. If you tried to cram the entire population into a single megastructure, the plumbing and power grid would fail. You distribute people across multiple apartment buildings to prevent that collapse. Data architecture works the same way. Instead of relying on one monolithic database, millions of user records are split across parallel shards: database A, database B, database C. But this creates an immediate vacuum. When a single user's request arrives at the data center, how does the system know exactly which isolated shard holds their data without wasting time guessing? Splitting the data solves the physical storage limits, but it creates a massive coordination overhead, a system that knows the data exists but has no reliable way to identify which shard holds it. This diagram shows a process called hashing. It's an algorithmic translation that takes any input, like a username, and outputs a specific integer. Dividing that hash number by your total servers gives a remainder. That remainder dictates the exact destination shard. Engineers call this modulo sharding. We've replaced searching with instant, rigid mathematics. Data rapidly snaps into its proper place without any lookup tables. But watch what happens when the network grows. Upgrading from 4 servers to 5 changes the fundamental denominator of our math. Because the formula is altered, almost every piece of data is suddenly assigned to a different server. It triggers a massive network migration, overloading the bandwidth and skyrocketing the risk of downtime. An architecture tied to fixed mathematical denominators is simply too rigid to survive real-world growth and truly massive global scale. To solve this, engineers shifted away from a rigid mathematical grid to a spatial, geometric map. They invented consistent hashing. Look at this glowing 360-degree circular map. This is the hash ring. Instead of linear bins, both the database servers and the hashed user data are placed onto the exact same circular perimeter. The routing rule is now universally simple. You locate the user's data point on the ring and move strictly clockwise. The first server you hit is where the data lives. Now, see how this geometry survives infrastructure growth. If you drop a new server onto the ring, only the tiny fraction of data immediately preceding it has to redirect to this new server. All other data on the ring remains totally static. Swapping linear math for circular geometry allows massive systems to expand their infrastructure without triggering a global reconfiguration, keeping any disruption localized. Still, there is a physical vulnerability. If servers are spaced unevenly, a massive gap forms, and one machine ends up absorbing a disproportionate amount of the clockwise traffic. We fix this with virtual nodes. It's like taking one central hub, breaking it into scattered outposts to distribute the load evenly. Instead of placing one physical server on the ring once, the system maps it dozens of times across various positions. Virtual nodes decouple the hardware limitations from the software topology. It guarantees a perfectly balanced load, regardless of unpredictable traffic spikes. Let's return to the exact moment you tap enter, only this time we're going to dive in at hyperspeed. Your request instantly clears the initial API gateway, where security rules and syntax are verified in microseconds. It slams into the initial cache layer, systems like Redis, for an immediate memory check before taking the time to query any deep storage. Missing the cache, the hash ring calculation executes. It applies the clockwise routing rule in a fraction of a millisecond to pinpoint your exact destination. And finally, the request strikes the one isolated, correct database shard out of thousands, completely ignoring the rest of the massive network. The username already taken warning is the final output of a high-speed routing engine, the mechanism that allows global platforms to maintain sub-second response times as they grow toward billions of users.